2023. Before that, me and my partner Emmanuel, we have been in the industry for more than a decade. So previously, I look at my brief, background. In 2019, I established the process safety research center for Wanhua Chemical, which is a specialty chemical company. And before that, I was technical director for DECRA process safety in US, in Americas. So before that, in 2017 to 2018, I was general manager for DECRA process safety in China, in Shanghai. Basically, I established a process safety consulting, testing, and training team in there. And before that, I was senior process safety specialist in DECRA in Princeton. So and other background. That's me. So this is our company, Prime Process Safety Center. What we do, we have three business sector. First one is process safety testing, and the second one is consulting, and the third one is training. So I'm gonna give you like about 10 minutes, very quick review what we're doing. First one is process safety laboratory. So we have a flammability gas liquid testing lab, and we do lots of tests such as flashpoint testing, UFL, auto ignition temperature, ROC, boiling point, melting point, and the P maximum kg. From there, we can get like laminar burning velocity, and also we have bond calorimeter. On right side, you can see lots of pictures for our testing equipment. So we also do like combustible dust testing, for any, relate to explosibility or combustibility of dust, we do test. And such as a go, no go, burning rate, KSTP maximum, MEC, ROC, MIE, MIT, and particle shape analysis, and also particle size distribution analysis, and moisture content analysis. So this, all testing equipment you can see from right side, the pictures. And we also do electrostatic hazard testing. The parameter we can test including volume resistivity, surface resistivity, charge decayation time, and breakdown voltage, liquid conductivity, flexible, FIBC, assessment, and also we do electrostatic chargeability test. So that with all this data, and we can quantitatively analyze in the plant, in the operation, what is like electrostatic hazard. So we also have reactive chemical lab. We have DSC, TGA, micro reaction calorimeter, accelerating rate calorimeter, and wind season package. As you can see, all these photos, it's live picture from our lab. And also we do self-heating test. As you can see, right side we have two carbonate oven, and we run basket test, air over layer, powder layer test, and bulk powder test, and also aerated powder test. From basket test, we can get powder in bulking form and at different size. When self-heating happen, what's the reaction kinetic looks like? With that data, we can help clients identify for a specific size of powder what is the critical ambient temperature which will create self-heating ignition issue. Previously, we just talked about process safety lab. Let's talk about process safety consulting. And actually, process safety consulting, we can do process safety management work, and also we help clients to do process safety engineering, such as like safety safeguard design and verification. So first, look at is like a process safety consulting, like a process safety management program. This is OSHA standard. which including 14 elements. We help clients, to first find the gap of process safety management, and also help clients improve process safety, management program. And also, if you don't have this program, we can help you establish a process safety management program for it. And for in the process safety management, the most critical element is process hazard analysis. And this process hazard analysis actually including several, level of analysis. For example, like HAZAP, LOPA, QRA, seal verification. HAZAP is used to identify the hazard, and the LOPA is to like a semi-quantitative analysis, say what safeguard, the level of safeguard you have, what is effectiveness, and with this safeguard, we call it, or sometimes we call it IPL. Not all safeguard are IPL, but IPL definitely is like a safeguard. And with all this IPL, what's the residual risk is. And also based on that, we can do quantitative risk assessment, which is detailed like numerical, risk assessment method, including consequence modeling. And, and with that, and we also perform seal verification, for functional safety. With so many IP around there, what is, safety integration level, and what's the gap between, the required safety level and what is the in the life, what it is, so what's the difference. So this is for HAZAP, LOPA, QRA, and the seal verification. What? Yeah. And we also do in process safety consulting. We also perform DHA. This is a major topic we're going to focus on today. So I just go through these pages. And we also do hazardous area classification, to help clients identify in the new operation how likely the plant will have flammable atmosphere, and also what's the extent of the flammable atmosphere. We also perform ignition source analysis. In the industry, there's many kind of ignition source, but the most powerful one, and also the very usually we can see in the industry, including like arc from electrical equipment. Basically, that's related to hazardous area classification. And as also you can see the electrostatic discharge. This happened in a lot, as ignition source in the industry. So we perform ignition source analysis, help clients. And otherwise, we can perform like a DIRS technology, use it to sizing rupture disk or pressure relief valve. And also we help clients design effluent handling system. Such as the right hand side, you can see this actually is a spotter distribution. We designed a quench pool for clients to handling pressure relief system, effluent. And we also perform like incident investigation. As you can see, the left side, there's two processes. You see on the top, the picture is like integrated, but the bottom, you see the pipe was burst. This is exactly from peroxide explosion, which split the pipe and have a big events. Right hand side, you can see two dust collector. One is integrated, another one is burned, right? So you see, like this type of incident, we are doing incident investigation very different with general, incident investigation. We go deep, dig the mechanism, and find the what exactly going on in the plant, in the industry, and help clients accurately identify what's the problem, and then recommend the accurate safeguard to what to do to prevent this thing happen again. And also, the third sector of our business to do process safety training, and we develop lots of process safety training course, but we're still expanding our training course scope. And from July, we're going to formal deliver our public training course, either virtually or like on-site. So that's basically what we're doing in Prime Process Safety Center. And this is the main content we're going to deliver for cost-effective DHA. First, I share some background, and then we talk about the combustible dust hazard, and also we're going to review NFPA 65.2. Nowadays is NFPA 660. I think probably many of you knows. And also, I will talk about three methods of dust hazard analysis, DHA, it's like prescriptive and performance-based DHA, and also risk-based DHA. And what is, the cost-effective DHA, how you should do it, because for DHA methodology, there's like quite controversial in the industry, like what method is best. And finally, we give the summary of our talk today. So first, to give everybody some background about incident that happened in the industry for from dust explosion. And you can see here, this is from Dust Safety Science, and the data is from 2022 Combustible Dust Incident Report. You can see in US, Canada, and international, and you can see from 2018 to 2022. The incident in US looks like a fire explosion, and also injury fatality goes down yearly. It goes down yearly. Look, this is like quite true because the U.S. put on us very strong regulatory requirement on the industry to prevent, dust explosion. And the Canada data is also driven a little bit down, but it's fluctuating. But globally, you can see the fire explosion incident, they jump back and forth. So you can, from this, you can say, globally, definitely dust explosion is a serious issue, and we should, pay attention on. So this is the bottom line is the figure for each month in 2022, and recorded like a different, incident. For example, like a fire, 2022 occurred 163, explosion of 50, injuries 89, fatality is 49. But we can say this is recorded, whatever can be recorded. But you probably everybody know incident occurs. Sometimes people don't expose it, and really, I mean, we don't know. So the actual data should be like far worse than the one we saw here. And from material point of view, you can say the most incident occurred, the material is like the in the food product. And second one could be like wood product, and third one could be metal or something else. We don't know. You can say. So actually, the incident dust explosions and occurred in the industry, like food is a lot. Food occupy big chunk of all of the incident. As you can see, from year by year, from 2019 to up to like 2022, this data has a little bit change, but do not have significant change. Uh, so which means the still food industry probably is the worst industry for dust explosion. And this is for industries. I mean, this matches with the previous data. We can say food, agriculture, and food product industry have a lots of, incident, that occupy almost 50% of other industry. As for equipment point of view, we can say the worst case, which is basically occupied. From here we can say very big. The worst equipment could be like a dust collector. Occupy big chunk of it. Dust collector. Second one could be dryer. Dust collector, and second one could be dryer. And third one is like a silo or like other storage, silo. So that you can say other thing like elevator, you see. So dust collector is like dryer and dust collector definitely is a big chunks of dust explosion. This from recorded data. And what's going on? This for equipment. So as for combustible dust, characterization, for all this combustible dust, for all these things, that before we do, any like dust hazard analysis, we have to know the material property, material combustibility or explosivity. So for all this, we like in US, we have SASTM standard for all these parameters, such as KST, MIT, either cloud or layer, and also minimum MEC, and also LOC, all these things. We have standard. In Europe, have different standard for it. So dust explosion hazard assessment method has been, controversial over the years. And the major concern in the industry is like a cost for DHA and also cost for testing, data, for get testing data. I mean, should we do all this test or we only need to do part of test? This is a cost. And also cost for improvement. How about after DHA is done and there is a recommendation, we need lots of, uh, installation, for safeguard, So combustible dust hazard, usually for combustible, everybody probably know, dust is if dust is combustible, and if we have fuel accident and ignition, this will only create a fire. For example, a pile of dust on the floor, and in the air environment, and if there's ignition source, it will give a fire. If we suspend the dust from a cloud in an open space, or in a enclosure in a room, however, the dust cloud concentration, the volume is very small. In that case, we will have flash fire because under this case, we have no pressure effect. However, if we suspend the dust in an enclosure, we have a confinement, like a big volume of combustible dust cloud in the occupied in enclosure, for example, in a like a equipment or in a room, that will create explosion. Between flash fire and explosion, the major difference is the pressure effect. However, from the mechanism point of view, like flash fire and explosion are the same. Basically, there is like a flame propagation happen in the suspended dust cloud. For combustible dust hazard, and there's several standards that covered it. For example, NFPA 654 covered general dust, and the NFPA 664 cover wood dust, and NFPA 484 cover metal dust, and NFPA 61 cover agriculture or food dust, and NFPA 655 covers sulfur dust. Since 2019, like NOPA have NOPA 652 and give like the methodology of dust hazard analysis, how to do it. And nowadays, all these standards combined together become NFPA 660. It was issued last year, and it is formally enforced in 2025, which is standard for combustible dust. This standard basically put all this standard together for all commodity, combustible dust put together, becomes one centralized standard. As you know, like in US, we have OSHA emphasize program, national emphasize program, which basically cite all refer to all this standard, and for OSHA auditor, go to onsite to do audit. And this is for commodity, dust. how requirement for different dust. However, for dust prevention and venting technology, and there's other standard also specifically talk about it. NFPA 68 talk about explosion venting. NFPA 69 is explosion prevention technology, and NFPA 60 talk about electrical code, how to prevent electrical ignition source. NFPA 77 is specifically talk about electrostatic ignition source. NFPA 499 basically specify how to classify area becomes like a class 2 hazardous area. Like in that classified area, the right electrical equipment should be selected and also be installed, follow NFPA 70, which is electrical code. That's basically for all codes and standard covered in the nowadays the standard. Let's do a quick compare between NFPA 660 and NFPA 652. As we know, NFPA 652 initially, issued, I think, in 2016 in that time frame, and the NFPA 660 is issued last year. And let's compare both of what's the content, what are the difference. You can see here, left side, I summarize NFPA 660, and then right side is NFPA 652. You can see from chapter 1 to chapter 9, they are almost, the same, even though the content inside have little bit difference, but essentially there are lots of content are very much similar, the same. However, in NFPA 660, the chapter 10 is talk about emergency planning and response. This chapter 10 basically took out from chapter 9 of NFPA 652, which is one section, in previous chapter 9. And the NFPA, from NFPA 660, chapter 21, talk about agriculture and food processing. Previously, it's NFPA, 60, that's agriculture, NFPA 61. And the chapter 22 is combustible metal dust. Basically, it's previously, NFPA 484. And chapter 23 talk about sulfur. Basically, it's previously NFPA 655. And chapter 24 talk about wood processing and woodworking, which is previously NFPA 654. So NFPA, like chapter 25, talk about general combustible dust. Basically, this is corresponding to previous NFPA 654. As you can see now, this NFPA 660 covered all previous, commodity combustible dust standard, becomes very bulky, standard combined together. It's more convenient, for industrial use. And let's compare like a chapter by chapter. Chapter 1, 2, 3 is most of them are general information and also definition. Chapter 4 talk about the general requirement, NFPA 100, NFPA 660, and NFPA 652. They are exactly the same. Structurally in the same way, and the content are very similar. And as for NFPA chapter 5, for hazard identification, and 1 and 2 are very similar. Basically, require to industry handle dust. You have to do combustibility and also explosibility test. However, in NFPA 660, there has a specific requirement for self-heating and reactivity hazard identification. In all previous standard NFPA 652 or NFPA 654, this part of information always keep as reserved, but in NFPA 660, this was specified. I'm going to take some time to explain this to everyone, okay? For combustibility and explosibility, they are very much the same, and also sampling. But here, for combustibility and explosibility test, I want to give a little bit more detail. So if a test goes to, we like recommend to do like a combustible dust go no go test. If it's a go, that means explodable. If it's explodable, actual, automatically the dust becomes combustible. However, if dust even show no go, that means if you ignite it, the flame cannot propagate. But you still need to go to combustibility test to identify if you have fire hazard or not. If you have fire hazard, then you will have like some specific requirement for it. So that means for all this standard, if we show no go, it doesn't mean you don't need to do anything. You still need to take care of fire hazard, to check if you have fire hazard or not. If you have, you need take some, yes, how to prevent or how to mitigate the fire hazard. For fire hazard, for combustibility test, NOPA 660 or NOPA 652 recommend to perform like a burning rate test using UNDOT testing N.1, test method for readily combustible solid. And this one, if it's show there is no reaction or no glowing, that means there is no, that means the material is not combustible. So this is combustibility test. So next one, and for self-heating and reactivity hazard identification, NOPA 660 gives specific, requirement, and which was not shown in previous, code and standard. For example, right now for self-heating hazard evaluation, and NOPA 660 require, for example, if you do bulk storage or transport, like combustible dust, which is you have quantity more than 1,000 kilogram or larger, under that case, you have to do self-heating hazard testing to demonstrate your material is not self-heating material. And also, if you have dryer and you have discharging bins and hoppers, if it's more than 10 kilo or higher temperature, then you also need to do self-heating, hazard evaluation. Or like if you went to DHA, if engineer point out you have self-heating potential, then you need to do it. For thermal instability, and also for more than 10,000 kilogram combustible particulate, if you stored longer than 8 hours and in a bin or hopper or at temperature higher than 30 degrees C, you have to demonstrate your thermal stability hazard. You have or you don't have thermal stability hazard. And also for like oven or dryer for more than 1 hour, if you have more than 100 kilogram material in there, and you also need to demonstrate thermal instability. Also, if there's a scenario from DHA that say there is a potential for thermal instability, you need to demonstrate. You need to, do this test, show their thermal instability is not an issue. Uh, the third one is for water reactivity hazard evaluation. And this also we need to do tests to demonstrate, the water-based fire suppression system is okay in your system. And also for particular product or dust, it can be, exposed to processed water, condensed water vapor, or outdoor precipitation. Under that case, you need to demonstrate that your material is water reactive or not. This type of things is very necessary because in the industry, for example, if you have aluminum dust, there's lots of incidents occurred. For example, you have outdoor dust collector, and at winter time, daytime you suck, air go in there. At winter time, that humidity, when temperature goes down and the hot air, humidity is high, and at winter and temperature goes down at night, and then it condenses in there. It will react with aluminum to form hydrogen. That's very flammable. This incident occur in the industry a lot. Another one is also check like a chemical reactivity hazard, which is basically address incompatibility of the material you are handling. Are you mixing to powder material, or is this material compatible with the construction of the equipment or whatsoever? So this is this for self-heating and the reactivity hazard was specified in NFPA 660. This is the first time we see NFPA address this issue. Previously it's always this part of content is always say reserved. So NLP for chapter 6, performance-based design option, and the NLP 660 and NLP 652 are very similar. And for performance-based design, for design criteria need consider life safety from fire and explosion hazard, and also structural integrity, right? If something happen, your structure is okay or not, and if it's not okay, then you need to consider, explosion venting of this, like building, room, whatever, and also mission continuity. So this is for performance criteria. As for design scenario and for performance design, if you are handling combustible dust, you always need to consider fire scenario and also flash fire and explosion scenario. This for performance-based design, this has to be considered. Okay, this is for performance based. And the NLPA 660 and NLPA 652, chapter 7, talk about the Sensen DHA, the methodology. And basically, if you look at it, like NLPA 660, NLPA 652, they are very similar. It's just in NLPA 660, it's worded in different way. For example, both of them require, DHA has to be reviewed and updated at every 5 years. And also for DHA, who is going to do DHA? The people has to be a qualified person, which means they have to understand NFPA codes and standard and understand the material property, and with experience, work on this field for quite a period of time. And as for methodology, generally both of them talk about it for combustible dust. The hazard that we have to identify is fire hazard, flash fire hazard, and explosion hazard. For a quantified DHA report, we have to first identify where you have hazard, either in the process equipment or external of process equipment, which means the building hosting the process. So first is identify hazard. If there is fire, flash fire or explosion hazard, do you have safeguard in the system? So we need to identify existing safeguard. If this safeguard is not enough, adequate enough to protect, like a life, like business community continuity, or like a building. In that way, we need to recommend additional safeguard to protect, the system. So basically, this DHA has to do all this. First is identify hazard, check what is existing safeguard, and do the recommendation. So this is for DHA. Whatever the method you use, we have to do these three things: equipment by equipment, pipe by pipe, and also in the for the building, hosting the process. So and chapter 8 talk about the management system. As you can see nowadays, for combustible dust, the management system very much similar with OSHA process safety management program. That's standard. So in the industry, actually PSM, the mindset or the methodology of PSM is very, very, good, which should be adopted by, general industry. And as for specific for combustible dust, if you look at all this, there the elements it's covered I put there's a tick. Basically every tick, this item corresponding to like process safety management program. One of element of process safety management program. So if we compare like NOP 660 and NOP 652, you can see for 660, they took out emergency planning and the response program out, and as additional chapter, which is chapter 10 in NFPA 660. But for all other states, you see here, like NFPA 60 add one operation readiness and review. Basically, this is like a PSSR, in PSM program. It's very similar. So this is like for management system. So that means if you're handling combustible dust, you need to have system in there to protect the system. Chapter 9 talk about hazard management, which is mitigation and prevention method. And you can say NOPA 660 and NOPA 62 are very similar, and with only one section in NLP 60 talk about risk assessment, the methodology. So that's why we usually say for DHA, there's three methods we should take. We can take. I mean, based on what you specific requirement. So as you can see, NFPA acknowledges three methods to do DHA. These three methods, but first one is a prescriptive method. So for this method, basically you need to go to on-site, look at how industry, how they handling combustible material, combustible dust, how they do it, and then work through in the plant and check what's the existing safeguard and what's the additional safeguard you should put it down. And as you can say, usually for prescriptive method, front cost is no. Basically, however, to do prescriptive, DHA, and the people who need this DHA should have well, good understand codes and standard, and being familiar with the equipment, whatever equipment in the plant. They should understand the process, understand the equipment, how it work, and also understand the code, what code and standards say. So usually the front cost is low, and improvement cost may be high because whatever you're doing, you need to follow standard, basically follow like codes and standard. So sometimes improvement cost could be high, and also as I mentioned, you need a qualified, knowledgeable DHA leader, facilitator, basically. Another method, like in NFPA chapter like 6, talk about performance-based design. Basically, it's a performance-based methodology. Usually, this one front cost is high too. Need lots of analysis and engineer calculation. I'm going to give you a case later, and also improvement cost may be low. It depends. Need a qualified, very knowledgeable senior DHA leader to complete this type of analysis. Another one is like risk-based method, which is also acknowledged in by NFPA. And the front cost sometimes can be very high and also very time-consuming, because the risk-based method nowadays industry usually use HACCP method to identify combustible dust hazard. For HACCP, you need a team of people sit together and go equipment by equipment, pipe by pipe, and lots of like time needed spending on like one knot usually take 2 and 3 hours, 2 to 3 hours. You can say there's lots of dedicating of people, and improvement cost maybe but sometimes it can be high too. When we run risk based, because for some of them, for example, like a whatever MIE, I mean, even larger than 1,000 millijoule. For example, we talk about MIE, and we talk about ignition source. And then for risk point of view, you still have risk. However, for prescriptive, if for some specific operation, if MIE is 1,000 millijoule, you can immediately say it's impossible. Electrostatic can be credible ignition source, something like that. And also this need a quantified very knowledgeable risk assessment DHA needed to complete. That means somebody should understand the principle of HACCP and understanding some the concept of LOPA, IPA or this type of things, and need a bigger team to complete. Facilitator needs to well understand HACCP LOPA principle. So in this, as you can see, this three method, and sometimes for some company they prefer use risk-based method. That means you have a team of people sit together. If for a big long process, this method may take a week or 2 week, and the clients will have like a, for example, process engineer, safety engineer, maintenance engineer, and sit together with you. It's very time consuming and cost can be very, very high. Because you need to dedicate so many time on there, and that's a major challenge in the industry, to use risk-based methodology. So this is like based on our experience, we recommend a cost-effective DHA, and for example, for a process, we would recommend first to do prescriptive method, and go to the on-site and check how you're doing, what you're doing, and to do for whole facility to check what safeguard you have, where do you have hazard, and based on that, we give recommendation what to do. And if all these recommendations are acceptable, then it's done. This can be done very quick, and cost is low too. And if for some for more specific operation, I'm going to give an example later, and then you may say, okay, then maybe cost is too high to do to follow prescriptive, recommendation from NFPA. Then we will identify for that specific equipment, we may do performance-based method. Say what's the hazard, what's the risk, to have combustible dust explosion. Or we can run like risk-based method for this specific equipment, and then check what should be done. If in that case, if risk is really low, I mean itself without any action, you don't need to do much, and then you're okay. Then that's will be okay. So this is for us for many years practice. We found that this is most cost-effective method to help clients solve their combustible dust handling process or facility. Uh, this quite makes sense, for DHA, what we do first, we need to check material hazard, material is combustible or explosible or not, and understand the process hazard, building hazard, and check a management system. So if you are handling combustible dust, then the overall we need to consider fire hazard, flash fire hazard, and also explosion hazard. Majorly focus on protect the life, property, and also business continuity. So, for example, and for do this DHA, we can first run prescriptive, compliance-based, approach. Basically, check, where is the header? Do you have protection? And is that protection adequate or not based on the code and standard? So this like a benefit advantage is like it's a checklist and can be done very quick, and the lowest upfront cost. That means the DHA cost is lower. And but the cons is like sometimes difficult to reconcile with operation, and sometimes a high capital cost for implementation of the recommendation. So under that case, I mean, the second method is performance based method, and this need detailed engineering analysis. The good thing is like sometimes low capital cost for implementation, and I said it's sometimes, not always. Okay, and the big cost is like a time consuming, it's very time consuming, and high upfront cost. That means somebody will go detailed calculation, may spend lots of time, and time is money. So risk-based approach is like basically consider likelihood and severity of the operation and say what's the risk and is this risk under the acceptable risk of the plant or not. So the good thing is like sometimes low capital cost for implementation, but also it's very time consuming as I just mentioned, and also high upfront cost for this one. You may spend like weeks, have many people stay together, many people their time is there's cost for everybody's time. So our recommendation is really when a prescriptive DHA identify gaps that are technically infeasible or require high capital investment, we pursue these two methods. Which one is more suitable? Okay, let's go to next one. So let's give you an example for cost-effective DHA. For example, in the NFPA, like recommend maintain adequate, for example, this process is like this dust collector, and there's many like hood to capture dust from the process through the duct work. Go to dust collector. This is the filter bag. Clean air exhaust through a fan and to outside. So, and also here, for example, there's a screw conveyor. This dust collected goes to screw conveyor and for dust disposal. For example, for this dust collection system, and if we follow NFPA recommendation, it says usually for general dust, and we need at least airflow velocity is around 18.5, at least 18.5 meter per second. This for airflow velocity. You say airflow velocity is higher and may need a bigger fan, or you need to, consume more energy, which is operation cost. And then if we, for this case, if, for example, if we use prescriptive measures, that means this task, this velocity we have to design high, gas flow velocity. However, if we consider saying, yeah, because we our fan at some situation is already, ordered, and they already being on site, and what you can do. So in this case, if it's hard to implement, then we can consider the performance DHA. But for performance DHA, basically we need to understand why we need a 20 meter per second or higher. Basically, in NFPA for this high velocity, the purpose of it is to prevent any dust accumulation inside the pipe. If you have dust accumulation, if something happen in the dust collector, this will resuspend dust and create a secondary explosion, which may burst the pipe, cause very catastrophic events. So basically, that's why NOP recommended the minimum carrier gas flow velocity. So we understand this performance, and then we can go to for a specific operation, and so we will look at what's the dust, particle density, and what's the terminal velocity of this dust. If this dust is very light, very easy to suspend, and we maybe 10 meter per second gas velocity can carry all dust. So under that case, we may not need, 20 meter per second. So this is based on the performance, as I just mentioned. You understand the parameter, recommended by NFPA behind what's the performance for that. If our specific dust can meet this performance, we can overcome this. So in that situation, you see, under this situation, and then if our dust is very light and we can prove, for example, 10 meter per second can carry dust and there's low dust accumulation in the ductwork, and we do, for example, at the very beginning, we do inspection every 2 weeks, and later on we do 1 month, 2 months, and found that there's no chance of dust accumulating in the ductwork. It meets the performance of low dust accumulation as required by NFPA. Then we meet this performance. We don't need exactly very high gas velocity. Then it still be operatable. Let's give another case. For example, another case is like this. This type of design will utilize in the pharmaceutical company. Sometimes in pharmaceutical company for API, if it's a very toxic material, and then what they do is like, for example, with filter like a dust collector as in container, and the clean air goes to the second dust collector majorly for toxicity point of view. They want this like a HEPA filter, and then release gas out. For this dust collector, because the gas collected barely have dust going here, and then for example, for in this case, do we need this dust collector be fully protected following NFPA recommendation? If we follow NFPA recommendation, because this is dust collector, you have to protect it. Whatever you do, right? You have to explosion venting, separation, isolation, whatever you need. And however, if we in this case, specific case, you see we have filter. If this filter in here was has like a pressure difference, interlock, lots of sense in here. In this way, we can do risk-based approach. For example, if this one formula, if we recommend this, for example, if this task is indoor, and what you do if we follow prescriptive method, this one you need to do lots of things. Maybe cost is very high, to do all dust explosion protection. However, in this case, we can run risk-based approach, and and then we will ask, for example, how much dust can be collected yearly, monthly, weekly in this dust collector. If the very few of dust you collected, that means in a year you barely can collect dust, which can create a dust cloud more than MEC. Under that case, the likelihood you have dust explosion hazard in this dust collector is very small. Under that case, you probably can be, avoid, costly, installation of, explosion protection or prevention stuff. Otherwise, like, for example, how often you do air injection to dedust from the filter? If you do very often, that means some dust can be suspended in the dirty side and may form exposable, dust cloud. And how to prevent back leakage of dust to downstream. You ask lots of questions and analyze this. For example, when the reverse air injection would be planned, and what action should be done during reverse air injection. What is likelihood of dust explosion in this dust collector? And we do all this analysis. We can run, based on the plant risk matrix, and we consider all these parameters, and we can run, say, do you have, is the dust explosion risk in here is acceptable or is lower than the tolerable risk in your plant or not. Based on that, we can rule for this specific dust collector, risk-based approach probably can help you exempt any dust explosion for this one. But it depends, how this system be operated, and what's safeguard you have in there. We call IPL. So in this case, probably for risk-based method will solve lots of issue on site. We did many this type of analysis for different company. So basically, that's all the topic. We prefer to use a hybrid approach. First at the beginning use prescriptive method, and then if something is hard to install or cost is very high, we go to like performance-based or risk-based approach for a specific equipment. So overall, this is summary. NLP codes and standard, widely recognized as a benchmark for Riga gap, and NLP 660, and previously it's like NLP 652, and provide many method, basically three methods to do DHA. and a comprehensive understanding of principle behind the NFPA requirement is really essential to perform, DHA, whatever method it is. I mean, three methodology offer the effective, method to minimize dust explosion, but it can be done, in a hybrid way, and that will help clients save lots of cost. Basically, that's all the talk today. And do you have any questions? And I can, uh, open some time for questions. Fred, can you unmute everyone? Say if they have any questions. Fred?
Sure, absolutely. If anyone has questions in the audience, please raise your hand and I'd be more than happy to unmute your mic so you get a chance to interact and engage with us. Okay, looking for raised hands. I'm not seeing any, so if you want to continue. Oh, never mind. I see one. Yep.
Yeah, two.
Okay, Denny, you're first. Unmuting you, or go ahead and unmute your mic.
Thanks for the section today. Really appreciate all the details. And I got a question or clarification on one of the slides about cost-effective DHA. That is the case study in dust collector in a risk-based approach, maybe 2 or 3 slides back.
Mm-hmm. This one, right, Danny?
Yeah, correct. I just want to clarify. So in this risk-based approach, meaning that means we can use a lot of qualitative approach, because this one I don't believe it is quantitative. So we can use a qualitative approach to do a risk-based assessment to prove that the system is working, or we need more engineering control, etc.
Yes, you are right. And based on what you have in the plan, for example, if you have your own risk matrix, and of course, to do this risk-based DHA, there's lots of detail we need to go through. Ask each finger scenario, and what's the likelihood, and what's the severity. But severity could be very high because it's combustible dust, right? But majorly it's likelihood, how many credit we can take. So it can be the best way to do risk assessment for this one is use a semi-quantitative, analysis. Some, integrate with LOPA method with HAZAP. That will be best, to demonstrate, your risk is low enough and you don't need to do anything. Yeah, I did several projects for a big car manufacturing company in Austin and last month, and it's very successful. Yeah. Okay, good. Thank you, Danny.
Hey, Denny, did you have anything else that you wanted to ask? Otherwise, Hossein, I see your hand raised. We're coming to you next.
Thank you. Thank you. First of all, Guibing, it's a nice presentation. I missed like the first 20 minutes. So is there any way we all participants can get your presentation? So that's my first question with regard to presentation, and then I have one like the generic question, which is in terms of like the kind of like a risk assessment tools, whether HAZOP or like the LOPA. So give me kind of like your experience, how like the performance based versus like the risk based, is there any like the depending like the whatever combustible dust, whether it's like the metal dust or like the aluminum dust or whatever industries you are talking. I think you partly answered in the previous questionnaires, but based on your experience, is there any kind of like the risk assessment tools, whether it's like the qualitative or like the semi-quantitative or like the full quantitative, how like performance based and like the risk based approach have like some more guidelines with regard to NFPA? Is there any recommendations they provided that would be helpful?
Okay, good. Thank you, Nur, for your questions. First one, I think we can share this PPT to everyone, and but in PDF form. And
Yeah,
the second,
thank you.
yeah, you ask a very good question. And as for risk-based, the software, for example, like a PHA Pro and PHA Works and some even spreadsheet can do this type of work, but as I mentioned, for risk-based approach, the best way from our experience is like combine both HAZAP and LOPA together to demonstrate your residual risk is low enough, it's reach the acceptable risk level of your plant. So in that way, it's best one. And if we just use quantitative analysis, sometimes kind of, vague and regulatory people look at your report, maybe feel this is like something, it's too quantitative. There is no data, prove, whatever you're talking, in that way, different people have different opinion, and sometimes it's hard to have, regulatory people to pass, whatever, your DHA method. As for performance-based design, this approach, and this basically did lots of engineered calculation for it. And performance-based DHA, it's not useful for all the operation. As you know, for this example, it's very easy to use because you have number, and you can easily plug to calculate your material based on your the material's property. And that this one is like a performance based, like a calculation is relatively easy to do. But for some other things, sometimes it's kind of hard. For example, for dust collector, like for some dust collector, if you do pressure containment, that means high pressure, requirement. That means you need to know exactly dust collector, for example, like a pressure, uh, like stress of dust collector, and also interconnected equipment or like a vessel. This type of things. Sometimes performance design, it's tough, but it's doable for a specific one. If sometimes we feel performance-based, method is not quite applicable, we tell clients maybe pursue risk-based is best. You know, of course, we recommend a prescriptive method to go first. For some specific, process, if it's hard to implement based on prescriptive DHA, then we pursue performance based. Yeah, performance based is it's just not, we need lots of engineering calculation, and many times we use like a spreadsheet can solve lots of can do lots of calculation too. And for other things, for example, if you have like a advanced tool, for example, Aspen, like a process of flow, design calculation, this type of software, that will be very, very helpful too. Okay. Hey, Nerd, and did I answer your question?
Great. Yeah, you answered very well. That would be helpful, and it's pleasure. Thank you for your answer.
Okay, thank you.
Well, if we have anyone else that has any comments, questions, or concerns, please unmute your mic, and the floor is open. Okay, it looks like we don't have any additional questions, and so I turn it back over to you.
Okay, so thank you everyone for attending our webinar, and hopefully, and we can meet somewhere, and we can serve your plans, whatever. Okay, you have a good day, everyone.